It's my pleasure to introduce Dr. Charles Chiu, who's a professor of laboratory medicine. He's also the director of the UCSF-Abbott Viral Diagnostics and Discovery Center and the associate director of the Clinical Microbiology Lab at UCSF. He's a board-certified infectious diseases physician and a leading investigator in sequencing clinical COVID-19 samples. He's a member of the Bay Area Lyme Scientific Advisory Board and has been working on Lyme and Lyme diagnostics for several years. Please join me in thanking Dr. Chiu for the work he's done on COVID and also on Lyme disease.
I'm going to go ahead and get started. I just want to thank the Bay Area Lyme Foundation, and I want to thank all of you for attending tonight. I want to start by talking about kind of what COVID-19 has sort of done to us, at least in the research field and also in the clinical field. It's completely upended not only the way that we treat or diagnose patients, but it really has upended the way we do research. And by that, I sort of mean that my entire research career has been devoted towards developing translational diagnostics. So my research involves studying emerging infections. I studied Zika virus, I studied Ebola virus. I studied a virus called enterovirus D68 that was associated with a rare syndrome called acute plasmomyelitis in children. And there have been several cases in California. And in addition to that, I have studied Lyme disease as well. And it's amazing to me that what happened, that we were completely still unprepared, having gone through all of these pandemic viruses, all of these pandemic pathogens. We already know about these emerging pathogens. And yet, we still aren't prepared, basically. And I distinctly remember what happened was when we first found out about the virus, at least in the United States, at the end of January, beginning of February, I was actually talking to my friend and colleague, who is actually a former postdoc of mine, Dr. Alex Greninger, who's currently is a professor at the University of Washington. He's in charge of their COVID testing program. And he was remarking how at the beginning of the pandemic, we didn't have a diagnostic for a novel virus. We weren't prepared. And in fact, he was actually, the initial screening that we did suggested that up to 20% of symptomatic cases were positive for COVID-19. And this was even before we knew that the virus was circulating undetected. And so that night, he actually sent me like a 2-text message, basically, we're effed. That's essentially what he said. I remember it's basically February 2nd, 2020. So I do want to talk about, I don't think I have my slides ready, but I do want to talk a little bit about how my research in Lyme disease has really helped us accelerate the work in COVID, and also vice versa. I've actually been working on Lyme disease diagnostics for the past 5 years, and some of it is funding from the Bay Area Lyme Foundation. So we've actually been interested in 2 different directions. So one direction was we've been interested in applying this technique called metagenomic sequencing. So what do I mean by metagenomic sequencing? Well, the idea is that any pathogen, any infection, is caused by an organism, whether it's a virus, it's a bacterium, a fungus, or a parasite. All of these organisms are made of either DNA or RNA. So, and the idea is, like, why not, instead of having to do test after test after test for individual organisms, why not do a single test by which you can diagnose all possible infections simultaneously? And this is especially important for tick-borne infections because it's not only Lyme disease, Borrelia burgdorferi, the agent that causes Lyme disease. There are a number of different pathogens that are found in ticks that essentially cause an indistinguishable disease. You can have fever, a rash, you could have chronic symptoms as well. They include Babesia, you may have heard of these, Anaplasma, Ehrlichia, Rickettsia, Bartonella, Tularemia. Too many to name. There are even some novel viruses that have been identified. So one is a virus called severe fever with thrombocytopenia virus. I don't know if any of you have heard of it. That's a tick-borne virus. And the first case was actually in the Midwest United States. Have any of you heard of Powassan virus by any chance? Anyone? Yeah, so you're probably from the East Coast, or at least you know people on the East Coast. But that's a tick-borne virus that has caused encephalitis cases. And so the general idea behind metagenomic sequencing is why not implement a single sequencing test by which you can actually take spinal fluid, you can take a sample of blood, you can take a respiratory secretion or perhaps some sputum, or you can take a little bit of fluid that comes from anywhere in your body and be able to diagnose any infection. So that's the general idea. And so what we've done at UCSF is we developed this test called the metagenomic next-generation sequencing test. And we initially developed it for spinal fluid, and we've been actually very, very successful in identifying cases of infection directly from spinal fluid from patients who have meningitis or encephalitis. These are neurological illnesses. I can tell you that we've had some cases, for instance, where we're able to diagnose Borrelia burgdorferi. We can identify the bacterium directly in spinal fluid. We can diagnose, we diagnosed a case of, several cases of Powassan virus. We've also diagnosed Balamuthia mandrillaris. You may have never heard of it. It's otherwise known as a brain-eating amoeba. But we can very easily identify this. And the idea is that we can do a single test. Now, there are a lot of challenges. You might say, well, this is so easy. Why not just implement the test? Well, I mean, the challenges are that one is that the test is very costly. And the test is also on very large instruments. So we have these sequencers. They're about $750,000 a sequencer. But it gives you the advantage that with each sequencer, I can literally sequence 3 billion reads a run. And by doing so, I can detect like the full spectrum of different organisms that cause disease. But what I wanted to do, and this is for Lyme disease, it's not sufficient to have just an expensive test because it's too expensive to run on everyone at any time. And what we've been really interested in doing is, can we make this test portable? Can I actually bring this test, make it cheap, make it say under $5 to $10, something that would be affordable, and yet can we do it in a way so that it potentially doesn't need to be done in the laboratory? Right? The idea would be, can we sort of deploy the test in, say, clinics, emergency departments, maybe even in point-of-care settings? Can we take it to the low-resource settings, maybe rural settings, and be able to run the test? And so we developed a new technology, and it's called nanopore sequencing. So this is basically where we took this technology. The nanopore sequencer is a pocket-sized device. And you can see the device there. It's actually powered by the USB port in your laptop. That's my postdoc, Dr. Wayne Dang, who's actually preparing the sample. It takes about 1 to 2 hours to prepare the sample. And what's amazing is that that's actually the most of the time. It actually takes from going from the sample to the library. But the idea is that once he actually pipettes that solution into the sequencer, you can actually start the run. And again, this is metagenomic sequencing. What I'm trying to do here is I'm sequencing all of the DNA and RNA in a clinical sample. Now, this happened to be a clinical sample from a patient who was bitten by a dog. You may guess what it might be, but that's actually the time frame. I'm speeding up a little bit, but it took us about 15 minutes from the time that we ran the test to make a diagnosis. And you can see here, I'm not sure if you can see on the bottom. Oh, you can see it. So this was rabies. Okay, and what's really interesting is so a couple of things is one that we didn't run this test here at UCSF. We didn't run it actually in the United States. This was run in Mali, where their resources are far limited. I can tell you the entire country of Mali has no test available for rabies. They can't even test for it. So what happens is if they have a patient who they think might have rabies, they have to simply just treat that patient empirically without knowing what the diagnosis is. And as you are well aware, that's the case for many tick-borne infections as well. So having the availability of having this kind of a test is going to, I feel, really transform the way we do diagnostics. I also want to mention that this particular test, the nanopore sequencer, we've been testing it on a wide variety of different tick-borne infections, and it's a direct detection test, meaning that we can run. We need to have some DNA or RNA from the organism that's present. But we have been able to run it, for instance, on samples from patients who have Lyme disease, who have anaplasmosis, who have rickettsiosis, Powassan virus encephalitis, and Bartonella as well. And so it's our hope and expectation that we could potentially translate this over into a clinical test. I want to actually kind of go from there to kind of the other thing that we're doing is that we're very interested in applying these sequencing methods towards, actually, before I talk about sequencing, why don't I talk about a new technology called CRISPR? How many of you have heard of CRISPR? Great, okay. You probably heard of it mostly for gene editing applications, for its promise, and indeed it's very, very good for gene editing applications. I'm using CRISPR in a slightly different way. I'm actually using it for diagnostics, because the same technology that allows you to target a gene with CRISPR what allows you to actually identify a pathogen using CRISPR. And so over the past 2 years, we've actually been working on a Lyme disease test that can actually use CRISPR to be able to identify an infection from Lyme disease in 30 minutes. But what's nice about it is that the test is not just for Lyme disease. It can identify Anaplasma, Rickettsia, Ehrlichia, etc. It's a single test for all of the pathogens simultaneously. And what was quite interesting is that when the COVID-19 pandemic turned about, it completely upended the way we do research. In fact, I was forbidden from doing any non-COVID research. However, I still could do COVID research. So what we ended up doing is the work that we took from Lyme disease, we had already developed at the time a CRISPR-based test for Lyme disease. So what we did is we took the same test and we actually ported it over to detect COVID-19. And so this is done in collaboration with a company called Mammoth Biosciences, which was founded by Dr. Jennifer Doudna, who won the Nobel Prize in Chemistry from UC Berkeley for discovering CRISPR. But I can tell you that we were partly because of our experience with developing Lyme disease diagnostics, we were able to go from just simply an idea to the actual running test in 14 days. And a few months later, we obtained FDA approval. It was actually the first CRISPR-based test to receive FDA EUA, not approval, but emergency use authorization for use as a clinical test. Thank you. So I want to end by talking about one last technology, which I think is going to be transformative in the way that we address Lyme disease. Actually, with respect to the diagnostic challenges between COVID-19 and Lyme disease, they really are not that different. We have diagnostic challenges with early Lyme disease, and partly because, as I already expressed, because there are so many other organisms that can cause a Lyme-like illness. And if you get bitten by a tick, you can have co-infections. And so it becomes very difficult of using single tests to be able to try to diagnose an infection because you may have multiple infections. And so that's the motivation for using metagenomics for early, and that's also why we're developing techniques like CRISPR, which can do this testing very quickly. But Lyme disease also has another aspect which is in need of diagnosis, and that is in diagnosing post-treatment Lyme disease syndrome, or what we consider perhaps chronic Lyme disease. I mean, the challenges are different, because I can tell you that with post-treatment Lyme disease syndrome, part of the reason why it's so difficult to diagnose is that we can't find the bug. We can't find Borrelia burgdorferi. It's very, very difficult. If we do try to find it, we have to, for instance, do very invasive biopsies. We have to get tissue. It's just not found in blood. The Borrelia bacterium is very quickly sequesters from the blood. And so the idea behind diagnosing this, and we do need diagnostics, because if we don't have diagnostics, we have no way of knowing, for instance, of being able to assess the efficacy of our therapies. We have no way of guiding clinical trials. Like, how can you tell whether a drug really worked if you have no tests that can monitor the disease or monitor where you are in the disease? So that's the concept behind this other approach, which also involves sequencing, and it's called host response. The idea is that any patient who's infected, who has an infection, has a host response. That's the patient's immune response or the patient's gene expression response to the infection. And they're really host responses to any acute illness. It doesn't even have to be an infectious illness. But it turns out that there's growing evidence now that you can actually diagnose infections not by identifying the organism, but by identifying a host response. And so I published several years ago, and this was actually with a former ELA winner, Dr. Jerome Bouquet, who is a postdoc at my lab. We published several years ago a study that showed that the host response to Lyme disease, at least early Lyme disease, is quite distinctive. It differs from other tick-borne infections. It differs from other infections like flu or bacteremia. And it's something you might expect because Lyme disease does in fact have some fairly distinctive characteristics. So we were able to show, for instance, that you can, by using the host response, you could actually diagnose Lyme disease up to a month following the acute infection, because you as a patient would still have the same host response. But the key question is, does the host response extend farther than that? Okay, so in this, we're actually doing a study, and this is in collaboration with the Lyme Disease Biobank, with Liz Horn, who's been fantastic with providing samples, but also with Drs. John Alcott and Mark Solosky from Johns Hopkins. They have a longitudinal study of Lyme disease where they enroll patients as soon as they get the tick-borne infection, present with a rash and erythema migrans rash and a fever, and they follow these patients these individuals for their patients for 2 years. So the idea is that we can now be able to look at host response, again, using sequencing, and by doing so, we could potentially diagnose chronic infection or post-treatment Lyme disease syndrome. And I have some actually very exciting data on very few patients, but I have some exciting data to show that in some patients who have chronic symptoms, you can detect a persistent elevated host response that appears to be specific to Lyme disease. And so this is data that we're currently writing up and publishing, and the idea is I envision that hopefully we will have a test that can be able to monitor post-treatment Lyme disease syndrome. And we're going to hopefully do it by sequencing. There's a lot to come, but this is kind of the next stage in kind of the work that we're doing. Thank you very much.